Collapse versus decoherence, unraveling quantum reality. The Schrödinger equation, a cornerstone of quantum mechanics, governs the evolution of the wave function psi, a mathematical object encoding the probabilities of outcomes in quantum systems. Two key interpretations of phenomena associated with this equation, wave function collapse and decoherence, attempt to explain how quantum probabilities manifest into the definite outcomes we observe in the macroscopic world. Below is a thorough analysis of both interpretations. Wave function collapse. Overview. The wave function collapse is central to the Copenhagen interpretation of quantum mechanics. It suggests that the wave function, which evolves deterministically according to the Schrödinger equation, undergoes a sudden, non-deterministic collapse into a single eigenstate upon measurement. Key features. Non-deterministic transition. Collapse introduces a non-unitary, probabilistic process inconsistent with the continuous evolution described by the Schrödinger equation. Role of measurement. The act of measurement is pivotal. It forces the system to choose one of its possible states. Von Neumann chain. Where does the measurement process end? The collapse hypothesis struggles to address the exact boundary between quantum and classical domains. Issues with wave function collapse. Lack of mechanistic explanation. Collapse is not derived from the Schrödinger equation, it is postulated separately. Ontological questions. What causes the collapse, and what does it imply about the nature of reality? Decoherence. Overview. Decoherence provides a mechanism to explain the appearance of wave function collapse without invoking a non-physical process. It describes how quantum superpositions are effectively destroyed by interactions with the environment, leading to classical-like outcomes. Key features. Decoherence arises naturally when a quantum system interacts with its surroundings, effectively entangling with them. No true collapse. The wave function of the system-environment composite remains intact and evolves deterministically under the Schrödinger equation. Apparent collapse is an emergent phenomenon. Branching universes, Everett interpretation. In interpretations like many worlds, decoherence explains the splitting of worlds without requiring wave function collapse. Advantages of decoherence. Derivable from Schrödinger dynamics, decoherence is a natural consequence of unitary evolution. Testable, decoherence effects have been observed experimentally, for instance, in interference experiments with increasingly complex systems. Challenges. Pointer basis problem. Why does decoherence select a specific set of preferred pointer states? Subjectivity of outcomes. While decoherence explains why superpositions are suppressed, it does not explain why a single outcome is perceived. Ontological status. If no collapse occurs, what determines the experienced reality? This question remains open, especially in non-collapse interpretations. Comparison and interplay. Concluding thoughts. Both wave function collapse and decoherence aim to address the transition from quantum superpositions to classical definiteness but approach the problem from vastly different philosophical and technical perspectives. Wave function collapse aligns with the Copenhagen interpretation, emphasizing the role of the observer and introducing non-determinism to resolve the measurement problem. It remains controversial due to its lack of a mechanistic foundation. Decoherence builds on the Schrödinger equation's deterministic framework, explaining classical emergence as a consequence of environmental interactions. However, it leaves open questions about the subjective perception of unique outcomes. The interplay between these interpretations reflects the deeper unresolved issues in quantum mechanics, including the nature of measurement, the role of the observer, and the fundamental structure of reality.